your hands and I'll call you out. Andre, go ahead.
Okay, thanks. I have a question to Gabor. Gabor, can you, towards the end of your talk, you made a statement. I just want to make sure I understand it correctly. Did you say that to see the transition between 5.5 and the anisotropic phase, you don't really need the pressure, you just should be able to control at atmospheric pressure, the width of the device and on down level mixing? Did I understand the statement correctly?
Well, that's what we think. So what we demonstrated is that with pressure, we can induce it. And what we think is that basically we are tuning these parameters, mixing and the width parameter. So the width parameter is tuned not because we are changing the width of the quantum well, but because the magnetic length changes with the density. So to demonstrate specifically what you're asking, we would need a sample that has a tunable density. The problem with these samples that we have is that the highest mobility samples typically are so heavily doped that they're ungateable. So we haven't done that, okay? So we cannot really tune the gate, the density through the gate in the samples that we have. And there is a second problem. So one thing that we don't understand is that somehow the nematic temperatures in the pressure cell are higher than in the sample with the ambient. I'm not sure if you remember, I showed that the other sample in the ambient, basically the nematic goes away at like 10 millikelvin. We cannot see it anymore. So it's extremely fragile. Somehow in the pressure cell seems to be more stable. Why is that? I'm not sure. Maybe there is a parameter that we haven't thought, or maybe there is like the disorder is a bit different when we apply the pressure. So this experiment would be extremely hard to do at this stage. But we suspect, based on the data that we have, that transition would occur. If you would be able to tune the density, we suspect you would see that.
But you also want to tune, or you will fix on down level mixing. So you fix magnetic field and tune density, that's what you're saying.
Right. Well, we tune the density and we just scan until we hit the right filling factor.
Right. Yes.
Right.
Okay. Thank you.
Okay, next question. Son, go ahead.
I want to ask Ramanjit about, can you construct the Moritz state in the same way?
Yeah, so if you start with this bilayer system with SU2, SU2, you just apply like flux attachment at the level of modular transformations. So then the resulting TP is the like U2 level 2, -4 times U1 level 2 up to some quotient. So this describes the fermionic Moritz state.
And the anti-Pfaffian and pH Pfaffian, can they be accessed in the same way?
So within this construction, so I think no, so I think so because they have different central charges for this bilayer construction, you wouldn't be able to access them within this bosonic theory because this always gives you something with central charge 3 has in the bilayer system. But in this sort of dual fermionic description, you can access these different fermionic states. So in particular, in this other paper that we have, where we look at sort of the dual fermionic side, there's a way starting from the free, so this is related to the duality that Hart presented on Tuesday with sort of an abelian fermion on one side to a non-abelian fermion on one side. And so you can, at sort of half filling, fill up lambda levels on the non-abelian side, which gives you the anti-Pfaffian state. And on the abelian side, at that filling, you have a metallic state. And if you assume the usual pairing, that also gives you the anti-Pfaffian. So within this bosonic description, it's not accessible, but you can sort of connect the dots in these different dualities to get different ways to access the anti-Pfaffian.
I'm asking that because I've been wondering, since the Pfaffian state comes in various flavors, could that also happen with the Retrezai state, that there is not just one k=3 Retrezai, but there are several of them? Can you access some of these potentially using some of these dualities?
So,
or argue that they must exist?
So in this bosonic description, you always just sort of get this sort of SE2 level K type topological order up to some U1 factor. I think in the sort of dual fermionic descriptions, you get slightly more complicated topological orders, like this U2 level K block when type states, which can, in principle, compete with these Reader's I states, I think. Yeah, I think that, that's a good question, so we didn't think about it too much for the Reader's I states, but in this dual fermionic description, the anti-Pfaffian emerges naturally, as opposed to the Pfaffian or particle hole Pfaffian. So that was something that we were confused about in the second fermionic paper that we had. So presumably, yeah, by connecting the dots with these dualities, it might be more transparent to get sort of generalizations of this family of Pfaffians to these Reader's I states.
Maybe I can just add one brief comment on this. So first of all, as far as the possible cousins of Reader's I, yeah, as Raman said, we hadn't thought in great detail about this. It's a really good question. We can, with sort of the variety of tools that we have, get essentially arbitrarily ornate things. In particular, we can get a lot of states with these different abelian and non-abelian levels that would sort of, principle, furnish these alternate Reader's I states. As far as which of those are sort of physical competitors in of Reader's I would need to think about that. Regarding the question of pH Pfaffian and anti-Pfaffian Pfaffian, yeah, as Raman said, we can get the anti-Pfaffian really nicely, and just to sort of mention explicitly, the fermionic duality encodes this as a duality between filling Landau levels on one side and pairing in the composite Fermi liquid theory. I think we can probably get pH Pfaffian and Pfaffian as well. It's just a matter of using different dualities from the one that we chose to emphasize in that paper. But there's no, I don't see any reason why we couldn't get the same thing for those.
Okay, the next question is from Duncan.
Yeah, so for distinguishing Pfaffians and anti-Pfaffians and stuff, I mean, you also don't have does the shift or the spin connection enter in the duality relations anywhere?
That's a good question. I think Hart has probably thought more about the geometric aspects of these.
Yeah, so we're actively working on this. So ordinarily, these dualities have a hard time encoding geometry in a natural way, because whereas global currents map to global currents very nicely as local operators on both sides. For example, the stress tensor doesn't have a nice local relationship between the two theories, but we still think that we can sort of reverse engineer the coupling to the spin connection on the non-abelian side, because at least for these fermionic theories, they have their own Jane sequences, and on those Jane sequences, you can locate an abelian state where you know what the shift should be. So you can design a coupling to the spin connection that spits that out, and then see what that generates for the additional non-abelian states on that sequence. Unfortunately, that's, yeah.
So the dualities, the field theory is really that they don't you haven't got that they're before Landau level projection, right? They're not
Right.
They're not quantum geometric theories. They're kind of contain the whole field theory, right?
Yeah, that's right. I mean,
they're fully local in the field theory language.
Right. You can say some things about the lowest Landau level limit, and actually we discussed this at some length in our
There should be any Landau level. I mean, it doesn't matter which Landau level you put any projection into a Landau level.
Right. So that's all I mean by lowest Landau level limit. So the question of projection we addressed in the context of these fermionic theories, because it turned out that there's a great deal of subtlety with those, where so the dualities are valid in the low energy limit, which is not the same as the limit as you project into a Landau level. And it turns out that the order of those limits is important as far as what state you get. So we ended up finding that there are several situations in which one theory, say on the abelian side, predicts an abelian state. And on the non-abelian side, you predict a non-abelian state.
So can you view I mean, so if you're dealing with like 5/2 or something, it shouldn't be included in this field theory type language. So, I mean, so would you say possibly what you're really doing is starting from a Landau level and unprojecting it by adding some kind of fake Landau orbit degrees of freedom or something? I mean,
yeah, you could sort of think of it that way.
Somehow logically, you should be really starting from a single Landau level. So the field theory is somehow ungeometrizing it or on the infrared scale, right?
That's right. It ungeometrizes it, and then you have to make decisions about how you geometrize it.
So essentially, you're introducing something like slave degrees of freedom to represent the orbital degrees of putting back. Well, I guess you so I've gone to a large scale, right? So your actual scale of these theories is huge compared to the magnetic length, right? It's on the macroscopic scale, right? You're basically ungeometrizing on a level much larger than the magnetic length. So reintroducing infrared locality.
Mm-hmm. Yeah, that's right.
Okay, great. I don't see any more raised hands. So if there's no more questions, then I'll hand back to the organizers.